Okay, why did I do that? Okay, so let's take roll. Barrett. Bessie. Burke. Kane. Dunlap.
Here.
Gallegos.
Here.
Ted.
Yeah.
Hollis. Irvin.
Here.
Leonard. Medina. Kylie. Medina. Manuel. Minisi. Kylie's here. Ooh. Okay, and Mosier is here. Orlando. Richardson, Jasmine.
Here.
Sieg.
Here.
Tillman. Ben Chapagada. Weflen.
Here.
And Wright.
Here.
All right. Okay, anybody else just walked in whose name I haven't called? Okay, so we're going to continue our discussion of kinetics. Let me just share my screen here. And remember correctly, the last thing we discussed was first order reaction. And let me go to the screen here. Remember, we covered zero order reactions and first order reactions, including how we determine the half-life. And we did this example. And I don't think I think the last slide that we covered was this slide. All right, so let me just continue from here. So, so this is showing you a plot. Now, I think it's probably best that I go back to this equation right here, which is basically the equation relating the concentration of a reactant to time for first order reaction. And if you recall, there you have two forms of equation which shows you the relationship. This is one form, and this is another way of basically saying the same thing. And I think I remember saying to you guys that we would use this equation if we want to find the concentration at a particular time. We would use this equation if we want to find T. And we use this equation along with this graph here to find the slope, which would give us the negative rate constant. So it depends on what you're trying to determine. Now, the reason why I went back to this particular slide, because this is basically a hypothetical example. And what I'm about to show you now, which I had before, is a real example of a first order reaction. This is the reaction right here. Right, this is the reaction, the decomposition of dinitrogen pentoxide to form nitrogen dioxide and oxygen. So somebody did studies with this reaction, looking at the change of concentration with time. And then what they did was find a natural log of the N2O5 and plot it versus the time. So the equation of the straight line graph that we're seeing here is okay, let me. So the equation of the straight line in this case would be the natural log of the concentration of N2O5 is equal to the natural log of N2O5 initial minus KT, right? So the equation of a straight line, which you guys should be familiar with from your previous math courses, you should recognize that this is in the form of y is equal to c minus mx, right? So m would be the slope, which is corresponding to, or I should say minus m would be the slope, which would be corresponding to minus K. And oh, I forgot to put O here. Remember, Ln2O5, O represents the initial concentration of N2O5. So basically, if you plot Ln2O5 concentration versus time, you're going to get a graph with a negative slope. As you can see here, this is a graph. And the slope, of course, would be minus delta y over delta x. All right? And that would be equal to minus K. Okay, so that's how you can get the rate constant. Here is the intercept on the y-axis that will give you the natural log of the initial concentration of N2O5. So let me just put that here. The natural log of the initial concentration of N2O5 would be the y-intercept right there. And therefore, based on that, you'll be able to find out what the actual initial concentration of N2O5 is, all right? So that's basically the graph of a real first order reaction and how you can determine the rate constant and the intercept on the y-axis. Okay, so let me see here. Okay, so let me get rid of this stuff right here. And let's look at this example. So this question says, it gives you the reaction and it says it's first order with respect to A with a rate constant of, and it gives you the rate constant at 80 degrees. So the question is asking, how long will it take for A to decrease from 0.88 m to 0.14 m, all right? So basically we can identify certain terms here. Turn on my pen again. So one term we can identify is the rate constant. So this here is the K, right? And the initial concentration of A is 0.88, and this is the concentration of A after the time has elapsed. And what the question is actually asking for is that time. How long will it take for the concentration to decrease from 0.88 to 0.14 m, all right? Now I think I have, okay, so the equation you're going to use in order to determine T is this equation right here, right? Because basically you have all the terms that you need to solve for T. So what I would do is, I would, of course, I identified already the initial concentration of A and the concentration of A after a certain time. So what I would do is do some algebra and rearrange this equation to solve for T. So T will be equal to what you see here. ln A initial minus ln A divided by K. And we can actually simplify this again based on what you should have learned in your math courses before you got here. You should recognize that this numerator part here is the same thing as this right here. ln initial A minus the concentration of A at time T. So basically all you have to do from here is plug the numbers in and you're going to get the time. Of course, the M units will cancel out. And when you plug your numbers into the calculator, you're going to end up with your time being equal to 66 seconds. All right, so that's basically how that is done. And also based on that example, well, let me ask first, any questions about this? Any questions? Yes, sir.
We're switching around the equation. You first add KT to both sides.
Yes, you add KT to both sides, and you also subtract ln A from both sides. And that's why you end up with this right here. And then to get from here to here, you simply divide both sides by K. All right, and then plug the numbers in. Okay, any other questions about this? Any other questions? Any other questions? Okay, so based on this example, oh, wait a minute, somebody, oh, okay, I'm just seeing your message, Kylie. I keep forgetting to check out the texting. Okay, so let me clear this and go to the assignment, because now we should be able to do, let's see here, assignment 2. So I'm quite sure there's at least one question we're able to do from assignment 2. I think we did this number 4 already. Okay, number 5. Actually, number 5 is dealing with the same reaction we just talked about. Of course, this is a glitch. This should be an arrow right here. And that's happens when I convert from Word to PDF. So this should be an arrow right here. All right. Okay. So in this question, they gave us the rate constant. So this is your K, right? And the question is asking, what is the concentration of N2O5 remaining after 2 hours if the initial concentration of N2O5 is 0.500? Now, as I said before, there are 2 forms of the equation that you could use. You could use this. I'm just going to use A to represent N2O5 because I'm lazy, all right? So A initial e to the minus kt. So this is one form of the equation you could use, or you could use the one that we just looked at earlier. Ln A is equal to ln A initial minus kt, right? So the question is, which form would you use directly? I would use this one, and the reason why is because the question is asking for the concentration of the reactant, and that is what this equation gives you, right? So I would say that the concentration of A would be equal to the initial concentration of A, which is 0.500 m times e to the minus kt. K is minus K is 6.32 times 10 to the minus 4 seconds to the minus 1 multiplied by the time. But you'll notice that the time is given in hours, all right? So what do you think we need to do as far as that is concerned?
For hours.
Exactly, you have to convert the hours to seconds. So how would you do that? I'm going to put 2.00 hours here, right? How do we convert the hours to second? What do we multiply that by in order to convert from hours to second?
By 60.
I'm sorry?
By 60 minutes. Right?
3,600.
Okay, yes, let's go with that. 3,600 seconds in 1 hour, all right? So basically, we'd have to work out this part first. So let me see what that gives. So 6.32 times 10 to the minus 4 times 2 times 3,600. So basically, this part here, according to my calculation, and again, please, if you think I've made a mistake, please feel free to correct me, all right? But this is what I got for this part right here. I got 4.55. And all the units will cancel out because the hours will cancel out and the seconds will cancel out. So there will be no units for this part. So what I'm going to do now is do e to the minus 4.55, which is 4.55 minus shift e, and then multiply by 0.5. And according to my calculation, I got 5.28 times 10 to the minus 3 m. So that's what I got for that. All right? Any questions about this? Any questions? Any questions? Yes, ma'am.
The negative 4.55 then exponent.
Yes,
Oh,
right, exactly. Okay, any other questions about this part? Okay, so I take it I can clear this, right? Right? All right, so let me scroll down now to B. Now B is asking, how long will it take, time required, for 90% of the N2O5 to decompose, right? Now, again, there are 2 forms of the equation that you can use. Let me just remind you of what the 2 forms are. You have concentration of A is equal to the initial concentration of A times e to the minus kt. And the other form is ln concentration of A is equal to ln initial concentration of A minus kt. All right. So my question to you is, which one of these two forms of the equation would you use to solve this question? And the hint is right here. How long will it take?
So the second with that.
Exactly, I would use the second one. So if you remember, when we rearrange this, we get T is equal to ln A initial over concentration of A divided by K, right? So the question now is, well, we know what the initial concentration of A is from earlier. That is equal to 0.500 M. I'm sorry, 0.500 M, right? This is the initial concentration of A. So we have this value here, and we're given K already. What was K? K was, what was K again? Can somebody remind me? 6 point what?
6.32.
6.32 times 10 to the
-4.
-4, and this will be seconds to the -1, right? Okay, so we know what this is, we know what this is. The question is, what is the concentration of A? And the hint lies right here. It says, at this time that you're trying to calculate, 90% of N2O5 has decomposed. All right? So the question is, what is the concentration of A? What do you think the concentration of A is equal to? If 90% of A has decomposed from the initial value was 0.500, then what do you think the concentration of A is at this point in time that you're trying to determine?
0.05.
Hmm?
0.05.
Okay, why do you say that? Let's hear the logic behind that.
Multiply 0.9 times 0.500.
I'm sorry, repeat that.
Multiply 0.9 or 90% times 0.500. And then take that number and subtract it from.
Okay, let's do it that way. So you're saying that take, repeat what you just said, I'm sorry.
So 0.90 for 90%.
Okay, so you're just gonna take 0.90 and multiply it by
0.500.
0.500 M, right? So this represents the amount that reacted, right? So that gives you what?
0.45.
0.45,
45.
okay. 0, well, okay, 0.45. And then what?
And then you subtract that from 0.500.
So therefore, the concentration of A would be equal to, let me do it down here. Concentration of A would be equal to 1 minus 0.45, right? So that gives you what?
0.05. 0.500 minus.
Say what?
We make 0.500 minus 0.
So this should be 0.5, I'm sorry, don't know what I'm thinking. So this should be 0.5. 0.500 minus 0.45 M. And that will give you you're right, 0.05 M. So basically, T will be equal to ln, the initial concentration of A, which is 0.500 M, divided by 0.05 M. All of that divided by K, which is 6.32 times 10 to the -4 seconds to the -1. And let's see what that gives. 4.5 divided by 0.05, and then I find the natural log of that. And then I divide that by 6.32 times 10 to the -4. And according to my calculation, now this I'd have to round off to 3 sig figs. So this would be 3.64 times 10 to the 3, according to my calculation. And the units here would be seconds. And that's how that would be done. All right? Okay, any question about this one? Any questions? Any questions? Okay, so if you understood B, then you should be able to do C. In fact, C is easier than B. Okay, can I clear this? In fact, let me clear just this here because again, we're going to use one of these two forms of the equation. So let me just erase this right here. Scroll down. Okay. This question is asking, how long will it take for 90% of the reactant to remain? So how would you solve this problem? Which form of these two equations would you use?
The second one?
Hmm?
Second one?
Exactly. So again, we rearrange this to get T is equal to ln A initial over concentration of A and all of that divided by K, right? So this time we need to find the concentration of A. How do we determine that? Because we know what the initial concentration is and we know what K is, right? So how would you find the concentration of A at that time? That's a hint right there, the 90%. How would you use that to find the concentration of A?
Well, it would just be 0.05.
I'm sorry?
Be 0.05. Because we kind of just found.
Well, the concentration initially was 0.05. I mean, 0.500, right? So it's 90%, which is 0.90 times 0.500 M, all right? So let's see what that gives, 0.9, oops, 0.9 times 0.5. So yeah, you're right, 0.045. 0.045 M, okay. So we just plug the numbers in, ln initial concentration, which is 0.500 M, divided by 0.0, I keep saying 0.45, and then divided by K, which is, what was K again, 6.32 times 10 to the minus 4, okay, seconds to the minus 1. Okay, so we do that calculation, 0.5 divided by 0.45, and then we find the natural log of that, and then divide by 6.32 times 10 to the minus 4. And according to my calculation, this works out to be equal to, when rounded off to 3 sig figs, 167 seconds. All right? And that's how that is done. Okay, any questions about this one? Any questions? Any questions? No questions? Okay. Let's look at D. Now, let me tell you something about D. There's a short way of doing it and a longer way of doing it. So let's hear what you have to say about D. Again, it's asking how long, right? And it gives you the percentage remaining, right? Now, we just met a term last class, which deals with the time it takes for the initial concentration of the reactant to be reduced by half. And there's a special name given to that time. What is that called? Half-life. And what's the formula for the half-life for a first order reaction? Feel free to look it up, even though you need to know it for your test.
ln2.
Half-life is equal to ln2 over the rate constant, right? So that's all you need. So in this particular case, half-life would be equal to ln2 over 6.32 times 10 to the minus 4 seconds to the minus 1. So natural log of 2 divided by 6.32 times 10 to the minus 4. And run it out to 3 sig figs. According to my calculation, the answer becomes 1.10 times 10 to the 3, and the units here would be seconds, and that's how that would be done. Right? Any questions about this? Any questions? Yes, sir.
The survey said I got 1.10 times 10 to the negative 5.
Okay, let me do this again. You're probably right. Come to think of it. Let me see here. ln2 divided by 6.32 times 10 to minus 4. No, I got 10 to the 3. So Folks, you have to be careful when using your calculators because when you're entering numbers like this in scientific notation, different calculators have different ways of inputting those kind of numbers, right? So it depends on your calculator. You may want to look at the handbook that comes with it in order to do this correctly, because if you can mess up your calculations if you don't know how to use it, all right? But that's what I got, 1.10, hold on, do this again. 2 natural log divided by 6.32 times 10 to the minus 4. Yeah, 1.10 times 10 to the 3, what I got, all right? Okay, any other questions about this? Any other questions? All right, let me see if there's anything more under this question. Okay, so let's move on or move back to PowerPoint. Let me clear this. And now we're going to talk about second order reaction. And that would be the final type of reaction in this series. So let me skip this thing, just do this thing. Okay, before we get to second order reaction, this is a graphical representation of the changes in concentration plotted on the y-axis versus time on the x-axis. And what you'll find is that for first order reaction, you have a smooth curve, and the curved line will approach the x-axis but won't touch it. We'll get closer and closer to it, but won't touch the x-axis, right? So as you can see here, the initial concentration of A is represented by the number of molecules in this representation here. After one half-life, then that is reduced by half. The concentration is reduced by half. After another half-life, the concentration is reduced by half, and so on and so forth, right? So basically, the half-life is constant. And as seen in the equation that we just used, let me remind you of what that equation is. In the equation of T half is equal to ln2 over K, right? K is a constant, and of course, ln2 is a constant, which means that the half-life for first order reaction is constant at all times, provided that the temperature is constant. That's a very important fact that you need to keep in mind when it comes to the first order reaction. That is not true, what I just said about the half-life being constant. That is not true for zero order reactions, right? In the case of the zero order reactions, the half-life is dependent on the initial concentration of A. And in the case of second order reactions, which we're going to look at shortly, you're going to see that there's a dependence also of the half-life in that case on the initial concentration of A. But in the case of first order reaction, that's not the case, right? So what you'll find is that I wrote down a little equation here, which basically is another way of expressing the relationship between the initial number of molecules and the number of molecules after a certain number of half-lives. So I use N here to represent number of molecules, but you can also use A instead of N for concentration. So I can rewrite this equation as concentration of A after a certain number of half-lives would be equal to the initial concentration of A over 2 to the N, where N represents the number of half-lives, which would be equal to the time elapsed divided by the half-life, all right? So basically, we can calculate the concentration of A using this equation, as well as what I showed you before. Concentration of A is equal to the initial concentration of A times e to the minus kT, right? So these are two ways of calculating the initial concentration of A. This is useful if you know what N is, and N would be equal to the number of half-lives, right? So I have a little table over to the right here, which shows you the relationship between the number of half-lives and the concentration of A, which would be equal to the initial concentration of A divided by N. Not the same N as this right here, but if the half-life here is, if the number of half-lives that passes is 1, then the concentration of A will be halved of the initial concentration, right, of A. If the number of half-lives is 2, then the concentration of A at that time would be initial concentration of A divided by 4. If the number of half-lives is 3, then the concentration of A would be equal to the initial concentration of A divided by 8, and so on and so forth. If the number of half-lives is 4, then the initial concentration of A would be equal to the initial concentration of A divided by 16, and so on and so forth, right? So basically, these numbers here are as a result of 2 raised to the n, right? If n is equal to 1, then we put a 2 here. If n is equal to 2, that's 2 squared 4, and so on and so forth, all right? So that's basically the relationship between the initial concentration of A and A based on the number of half-lives, all right? Okay, and that's basically it as far as first order reactions are concerned. So let's look at second order reactions. So in the case of second order reactions, where you have the reactant forming the product, the rate law would be this right here. Rate is equal to K times the concentration of A raised to the second power, all right? Now, based on this equation right here, we can figure out that the units of K, well, K would be equal to rate divided by concentration of A squared. If the units of rate is M over S and the unit of molarity is M, then basically we can determine what the unit of K would be for second order reactions, and that would be equal to 1 over M times S. Or another way of expressing this would be M to the minus 1, S to the minus 1, right? So this and this are basically saying the same thing. Also, please note that the unit of time is not necessarily going to be seconds. It could be literally any unit of time. It could be minutes, it could be hours, it could be years. It doesn't matter. It depends on, again, how fast the reaction progresses, all right? Okay, so continuing. So basically, as I said before, this is the rate law here. And because rate is equal to minus the change in concentration of A over change in time, we can set this equal to this. In other words, we're going to end up with this. And again, there's some calculus involved. I won't go through all the steps. You're going to ultimately end up with this equation right here, right? And this equation here relates the concentration of the reactant to time for a second order reaction, right? So it's 1 over the concentration of A at that time is equal to 1 over the initial concentration of A plus K times the time, all right? So that's the equation which relates the concentration of A to time. And so just to define the different terms, this is the concentration of A at time t. A0, or concentration of A0, is the concentration of A at time equals 0. And we can calculate the half-life for a second order reaction. Remember, the half-life by definition is the time it takes for the concentration of the reactant to fall to half the initial value. So we substitute T half where T is, and we substitute this term where A is, and I won't go through all the steps. Basically, you're going to end up with this equation here. The half-life for a second order reaction is equal to 1 over K times the initial concentration of A. And again, as in the case of a zero order reaction, the half-life is dependent on the initial concentration of A, all right? Another thing I want to mention too is that we can graphically determine what K is based on data collected for the concentration of A and the corresponding times. Basically, what you'd have to do after you collect the data for the concentration of A and time, we divide 1 by the concentration and we plot it versus time. That's what's shown here. 1 over the concentration of A at different times versus time. You're going to get a straight line graph. And if you look at this equation here, you can see that this equation is in the form of a straight line with a positive slope. So 1 over A, oh shucks, what's going on here? Okay, so this would be the Y, this would be the Y value, T would be the X value, this would be the intercept on the Y-axis, and K would be the slope, right? So we can use data, if we know what the concentrations are at different times, we plot 1 over the concentration versus time. You're going to get a straight line graph for which the slope would be equal to rate constant, and the intercept would be giving you the 1 over the initial concentration of A. All right? So that's basically it for the second order reaction. And do I have an example of this? Yes, ma'am.
What is a,
What is what?
a to the second power on the right-hand side?
Well, this is the rate law for a second order reaction, right? So if it's second order, that means that the concentration in this equation, the concentration of A would be raised to the second power. All right? Okay, any other questions before I move on from this slide? Any other questions? Okay, I thought I had an example here. So let me go to the assignment again. And let me clear this. Okay, so this question, scroll a little bit. This question says, well, let me write down the equation first that you're going to need. So this is for a second order reaction. 1 over the concentration of A is equal to 1 over the initial concentration of A plus KT. So that's the equation you're going to use, right? So the question says, it's talking about the rate law for the dissociation of iodine. Well, that's weird. Something is not right here. Oh, it's right. Okay. So you're going from, it's not dissociation, it's a reverse. It's the association of iodine atoms to iodine molecules. And the rate law is given as this, right? So obviously this is a second order reaction. They also gave you K. Interestingly, they did not give you the units, right? In fact, the A part is asking for the proper units of K. And of course, we know that the units of K from the previous slide was m to the minus 1, s to the minus 1, or 1 over ms, right? So that would be the answer here, m to the minus 1, s to the minus 1, all right? So this question is asking, if the initial concentration of the reactant is 0.40 m, calculate the concentration of I at that time, which is given as 2.5 times 10 to the minus 7 seconds. So basically, we'll be using this equation right here, right? So we can say that 1 over the concentration of A will be equal to 1 over the initial concentration, which is 0.40 m, plus K, which is 7.0 times 10 to the 9. And this would be seconds, I'm sorry, m to the minus 1, s to the minus 1, times the time, which is 2.5 times 10 to the minus 7 seconds, all right? So that's basically it for calculating 1 over the concentration of A. What I'm going to do is work out this part first. So 7 times 10 to the 9, I'm going to multiply that by 2.5 times 10 to the minus 7. Okay, so according to my calculation, rounded off to 2 sig figs. This part here would work out to be 1.8 times 10 to the 3. And the units here would be m to the minus 1. And that would be added to 1 over 0.4. So let's see what that gives. 0.4. Okay, so according to my calculation, this works out to be 2.5 times, well, 2.5, I'm sorry. That's it. Let me erase this here. So this would be m to the minus 1. So we have to add these two. Now, what I would do in order to make sure that I'm able to round the final answer to the correct number of, in this case, decimal places, I'm going to express this in a similar fashion to this, where the exponent is 10 to the 3. So if this is 10 to the 3, right, that means that I would have to move the decimal point 3 places to the left. So that would be 0.0025. M to the minus 1 plus 1.8 times 10 to the 3. So basically all I have to do is add 0.025. 1, 2, yeah, this should be 0.025. Let me erase this here. This should be 0.025, and I'm gonna add that to the 1.8, right? And I will end up with 1 over concentration of A is equal to 1.8 times 10 to the 3, right? Because when you're adding this to this, you're going to get, in fact, let me show you what you're going to get, and then I'll show you how I round it off. You're going to get, on your calculator display, you're going to get 1.8 25m to the minus times 10 to the minus times 10 to the 3 times 10 to the 3, but you have to round off to 1 decimal place here. So you have to round off the coefficient to 1 decimal place. So when rounded off correctly, you're going to end up with 1.8 times 10 to the 3 m to the minus 1. But we're not finished yet because the question is asking for you to calculate the concentration of A, which would be 1 over 1.8 times 10 to the 3 m to the minus 1. So let me do that. 1 divided by 1.8 times 10 to the 3. And according to my calculations, when rounded off to 2 sig figs, they're going to get 5.6 times 10 to the minus 4 m. And that's basically how that is done. All right? Okay, any questions about this? Any questions? Any questions? Okay, I think there are other parts to this question. Let me clear this. Scroll down. Okay. It says if the initial concentration of A is 0.50 m, what is the half-life? Now, can somebody remind me of the formula for half-life for a second order reaction? Half-life is equal to what? Feel free to look in your notes.
1 over
1 over K times.
initial concentration.
Okay, very good. So that's it. K is given as, remind me. From earlier, from
7.0 times
7.0?
Yeah, times 10 to the 9.
Oh, times 10 to the 9. And this would be m to the minus 1, seconds to the minus 1, times the initial concentration, which is 0.40 m. So let's see what that gives. 7 times 10 to the 9 times 0.4, and then 1 over that. Where's that key? Oh, there. Okay, so according to my calculation, this works out to be 3.6 times 10 to the minus 10, and the units here would be seconds. I don't know why I put m there. This should be seconds. All right, because this will cancel with that. This is s to the minus 1 down here, so that will flip up to s at the top. All right?
Is that a -10 exponent?
Yeah, minus 10, yeah. Okay. Any questions about this one? Any questions? Okay, in the case of D, it says if the initial concentration is 0.80 m, how much time would it take for 75% of the iodine atoms to react? So the equation you're going to use for this one, I'm just going to put it in this box over here, is 1 over the concentration of A is equal to 1 over the initial concentration of A plus KT, right? So what the question is asking for is time, right? So what I would do is rearrange this to get KT is equal to 1 over the concentration of A minus 1 over the initial concentration of A. And then I would solve for T. T would be equal to 1 over K times 1 over the concentration of A minus 1 over the initial concentration of A, right? And the key thing, because we know what K is already, K is what we use here, and we know what the initial concentration of A is. What we don't know directly is the concentration of A, but we have some information here that can help us. So how would we determine the concentration of A? It says, how much time would it take for 75% of the iodine atoms to react? So the concentration of A would be equal to what? If 75% of the iodine atoms reacted, then how much remain? 25%, right? So basically the concentration of A would be 25% of the initial amount. So it's 1 minus 75% or 0.75 multiplied by the initial concentration of A. So that would be 0.25 times 0.80 M. So that would be a quarter of 0.8, which would be 0.20 M. All right. So now we can plug the numbers into this equation. So T would be equal to 1 over K, which is 7.0 times 10 to the 9, M to the minus 1, S to the minus 1, multiplied by 1 over 0.20 M minus 1 over the initial, which is 0.80 M. And that's the setup. So let me work out what's within the parentheses first. So that's 0.2, 1 over that, minus 0.8, 1 over that. Okay, so I got 1 over 7.0 times 10 to the 9, M to the minus 1, second to the minus 1. So what I got for this part, and please correct me if I'm wrong, I got 3.75 M to the minus 1, right? And then I'm going to divide that by 7 times 10 to the 9. And I got, wrote it out to 2 sig figs, I got 5.4 times 10 to the minus 10 seconds, right? Because again, this will cancel out with that, all right? So that's basically what I got, all right? Okay, any questions about this one? Any questions?
Why does the seconds lose the -1?
I'm sorry,
The exponent,
you mean here?
like the second says -1 above it, and then for your refinements, we just get rid of it.
Because after this cancels over this, you're gonna have 1 over S to the minus 1, which is basically the second thing. You have a question?
Yeah, does that say 3.75 M to the minus 1?
M to the minus 1, yeah. Mhm. Okay, any other questions? Any other questions? Okay, let me see if there are any more questions, any more parts to. Okay, so that's it as far as that is concerned. So let me clear this and go back to the PowerPoint. Okay, so on this slide, I have a summary of the equations that you need to know for the 0, first, and second order reactions, right? So these are basically all the equations which relates the concentration of the reactants to time, all right? Well, this would be the rate laws for the 0, first, and second order reaction. That's very easy to remember, all right? These are the equations which relates the concentration to time for each of those types of reactions. And these are the equations which gives you the half-lives for, again, 0, first, and second order reactions, all right? And again, let me remind you that in the case of the first order reaction, it's constant as long as the temperature is constant because there's no concentration term present in that equation. In the case of the 0 and the second order reaction, we have the initial concentration involved in each of these equations. So in the case of the half-life for 0 and second order reactions, they are dependent on the concentration, the initial concentration of the reactant. That is not true for the first order reaction, all right? Okay, so now that we have discussed all of that, I want to move on now to looking at how temperature affects the rate of reaction and how we can explain that at the microscopic level. So what you're looking at here in this slide is, a general hypothetical situation where there's a one-step process where the reactants are converted to products. All right, so the reactants are A and B, and the products are C and D, right? And basically, in order for the reaction to take place, A and B need to combine to form, and you're going to see this term later on, but I'll tell you now, it's called an activated complex or a transition state. Both terms are used interchangeably, right? And then after that is formed, then the product C and D will be formed, right? So this is representing what is happening in the case of an exothermic reaction. And I'm quite sure you guys are familiar with those terms, exothermic and endothermic from your General Chemistry 1 course, right? Exothermic reactions, as you go from reactants to products, will lose heat energy, all right? So will generate heat, while an endothermic reaction, as you go from reactants to products, will absorb heat from the environment, right? So this is what we call the energy diagram for an exothermic reaction, right? You'll notice that the energy diagram is basically a plot of the energy versus the reaction progress, right? And you'll notice here that the energy of the products will be less than the energy of the reactant. So therefore, there's a loss of heat energy as you go from reactant to product. Over here, it's the opposite, right? The energy of the products are greater than that of the reactants. So as you go from left to right, as you go from reactants to product, heat will be absorbed from the environment as you get to the products, which will have a higher energy value compared to the reactants. So that's what happens in the case of an exothermic and endothermic reaction, respectively, all right? So what we're going to look at is, let me point out one important feature of both of these graphs. In order for the reaction to take place, as I said before, the transition state would have to be formed, right? And therefore, energy would have to be absorbed as you go from the reactant to the transition state. The same is true for both exothermic and endothermic reaction. That energy that is needed to form the transition state from the reactants, we call that the activation energy, right? So the activation energy, as stated here, the definition is, it is a minimum amount of energy that the reactants have to get or have to absorb from somewhere in order for the reaction to take place, right? If the reacting molecules cannot get that energy, then the reaction will not take place, all right? So that's a very important aspect of energy changes that is taking place in any chemical reaction. And you're going to see the relationship between the activation energy and temperature and the rate of reaction, all right? So in order for us to understand in more detail what we just discussed, you have to be introduced to what is called the collision theory. And basically what this theory says is that in order for molecules, reacting molecules, to react, they must collide, all right? Which makes sense. If you think about it, if you use your imagination, then you can understand that there must be some contact that will occur when you have reacting molecules reacting to form products, right? But the thing about the collision theory is that it specifies that in order for the reaction to take place, the reacting molecules, when they collide, they must have that minimum activation energy, because energy will be needed to break bonds, and then energy will be released when bonds are formed, right? So for the initial breaking of the bonds, the reacting molecules, when they collide, must have at least that minimum activation energy before the reaction can take place, right? And the more molecules that will have that activation energy, the faster will be the rate of the reaction. Now, this graph that is to the right of the screen shows you the fraction of molecules, a plot of the fraction of molecules with a certain kinetic energy versus kinetic energy, right? And this line here represents the plot when the temperature is higher compared to this plot when the temperature is lower. So T1 is less than T2, or T2 is greater than T1, right? Now, this shaded part here, right, for T2, basically represent the number of molecules which have this amount of energy. So let's say this here is the activation energy. So let's say this here represents the activation energy, right? Then the shaded part right here under the blue line here represents the number of molecules that have at least that activation energy, right? That's for when the temperature is T1. Now, if you increase the temperature to T2, what happened is that the area here is greater, right? That means more molecules will have at least the activation energy, which means that the reaction rate ultimately will increase because you have more molecules now having the minimum energy required for the molecules to collide and then form products, all right? So basically, the conclusion we can come to based on just this discussion right here is that the higher the temperature, the more molecules that will have at least the minimum activation energy, and therefore the reaction rate will increase, all right? And from our everyday experience, we know that to be the case. The higher the temperature, the greater the rate of reaction. For example, the spoilage of food, right? That's a chemical reaction, and we all know that at higher temperatures, the spoilage will occur at a faster rate, all right? So that's just one example, and there are several other examples we could point to, all right? Okay, so this is basically a qualitative description of the effect of temperature on the rate of reaction. But we can have a more, let me clear this here. We can have a more quantitative description, which I think is what this slide is all about. Okay, so this is just reiterating what the activation energy is. Okay, so I forgot that this slide was here. Another important aspect of a successful collision between molecules to get products is the orientation, the relative orientations of the molecules that are reacting with each other. Now, this particular reaction, for those of you who have to do organic chemistry, will be very important, all right? So basically what is happening here is a reaction between this molecule, which is known as bromomethane, reacting with this. Now, this is actually not the iodine atom, but the iodide ion. So let me put a negative charge on this. So this is going to be carrying a negative charge, right? Now, based on, the theoretical concept of spatial orientation affecting reaction rate, right? One would consider the iodide ion approaching this molecule to where the bromine is, or it can be approaching to where the carbon is, because the actual reaction is this. I probably should have said this before. The actual reaction is, just squeeze this up here, CH3Br plus I minus to give CH3I plus Br minus, all right? So basically, just based on what we're looking at up here, basically this bond between the carbon and the bromine must be broken, and a bond between the iodide and the carbon must be formed. Now, the thing about this approach is that this is highly unlikely because the bromine here has a partial negative charge. Because bromine is more electronegative than carbon, there'll be a separation of charge within that bond, and therefore the bromine will have a partial negative charge, right? And as we all know, like charges don't like each other, right? So therefore, this approach, where the iodide is approaching from that end of that bond, is less likely to occur, right? What is more likely to occur is the iodide ion approaching this carbon here, because now this carbon has a partial plus charge. At the same time, this pair of electrons here will leave with the bromine to form the bromide ion, right? So the important point I'm stressing here, using this example, is that in some reactions, in fact, I would say in most reactions, the spatial orientation of the molecules relative to each other is important in order for a successful reaction to take place, all right? So that's basically another aspect of the collision theory to explain the successful formation of products from reactants. Okay, any questions about this? Any questions about the collision theory? Any questions? Okay, let's check something here. Okay, so I think the next slide is where we have, let me clear this first. Okay. So let's see, the next slide is showing you an energy diagram, again, highlighting and emphasizing the importance of the transition state as it relates to the energy diagram. So this is another reaction, let me write down the equation for this reaction. Let me do that up here. The reaction is between carbon monoxide and nitrogen dioxide to form carbon dioxide and nitrogen monoxide, all right? So just based on what you can observe here in this equation, in order for this reaction to occur, you must have the transfer of an oxygen from NO2 to carbon monoxide. So you're going to end up with CO2 and nitrogen monoxide. So this is what this energy diagram is showing. It's showing you how the energy changes as you go from the reactants to the products, right? So over here, we have the carbon monoxide molecule and the nitrogen dioxide molecule. And basically, energy is required in order to get to the transition state. Now, the transition state is what will occur when you have the simultaneous transition, or I should say, the simultaneous transference of the oxygen from the NO2 to the carbon. So basically, you're going to have a bond being formed between the carbon and the oxygen, and simultaneously, you're going to have a bond being broken between the nitrogen and the oxygen, right? So the transition state will basically be a structure where you have the oxygen simultaneously linked to the carbon of the carbon monoxide and the nitrogen that was a part of the nitrogen dioxide, right? So this structure here is called the transition state. And an interesting thing about the transition state for reactions is that, and I can only say to the best of my knowledge, the important point about transition states is that you cannot isolate them, right? You can only infer their structure based on the reactants that are involved. And I have to say that to date, as far as I know, nobody has been able to isolate the transition state of any reaction. I may need to research that to see if that is still the case, but as far as I know, that is the case, all right? So this is a transition state, right? We inferred structure based on what we're starting off with. And of course, a certain amount of energy is needed to get from the reactants to the transition state. And that would be the activation energy, which in this reaction is equal to 134 kilojoules, right? And then what happens is that you have the complete formation of the carbon to oxygen bond. Simultaneously, you're going to have the complete breaking of the oxygen to nitrogen bond. And that would result in a release in energy until you get to the products down here. And here we have the carbon dioxide molecule and the nitrogen monoxide molecule, which are the products, all right? And we can determine based on the energy diagram, the enthalpy change for that reaction, which would be equal to the energy of the products minus the energy of the reactants, which would be equal to minus 226 kilojoules. So that's basically it as far as looking at the energy changes as you go from the reactants to the products. And you can also look at things going in the reverse direction, right? Now, going in the reverse direction, again, the activation energy would be the difference between the reactants and the transition state energy. If you're going in the reverse direction, these products would now be the reactants, which means that the activation energy would be the difference between the energy of the product here and the transition state. And therefore, that would be equal to 360 kilojoules, right? As far as the enthalpy of the reverse reaction, it would be plus 226 kilojoules because you're going in the reverse direction, right? And that's basically how that works as far as the collision theory is concerned. Another term for the transition state, it's called the activated complex, right? So you can use those two terms interchangeably. Okay, and as I said before, the activation energy is the difference between the energy of the transition state and the energy of the reactants, which, as I said before, is equal to 134 kilojoules for the forward reaction, all right? And I gave you this already. This is the heat of the reaction, which is the difference between the enthalpy of the products and the enthalpy of the reactants. Okay, so I talked about the fact that, clear this first, that the, oh, wait a minute. Let me see if there's a question we can do. Oh, not yet, okay. We can't do number 7 yet, so let me go back to the PowerPoint. Okay, so let's look at, in a more quantitative fashion, the relationship between temperature and the rate of reaction. And a guy, very important chemist, by the name of Arrhenius, he proposed this equation, which relates the rate constant for the reaction and the temperature. K is equal to A times e to the minus EA over RT, right? Now, let me go back to this here, I'm sorry. So if you, based on this equation, if you were to plot the rate constant of the reaction versus temperature, you're going to get this curve right here, all right? So this curve is basically a plot of this equation. Now, let me define what each of these terms mean, right? So this is the Arrhenius equation. EA is the activation energy. So remember, the activation energy is the energy, minimum energy that the reacting molecules need in order for successful collisions resulting in products. R is the molar gas constant, and the form of the molar gas constant you're going to use is this right here. So not the other form, which is 0.0821. You're going to use 8.31 joules per Kelvin per Kelvin mole. I'm sorry. And T is the temperature in Kelvin, right? And A is what is called a frequency factor. All right. And another way of expressing this equation, which is more useful in terms of graph plotting, if you find the natural log of both sides, I won't go through all of that. Again, this is some algebra which you need to be, you should understand based on your past math experience. If you find the natural log of both sides, you're going to end up with this equation here. ln k is equal to minus EA over R times 1 over T plus ln A. And if you inspect this equation carefully, you'll see that this will be an equation of a straight line where ln k would represent the y values, the 1 over T would represent the x values, the minus EA over R would represent the slope, and the ln A would represent the value on the y-intercept, all right? So basically, if you were to plot ln k versus 1 over T, you're going to get a graph looking like this, straight line slope with a straight line graph with a negative slope, where the slope is equal to minus EA over R, and the intercept, which is not shown here, would be ln A. So basically, when you plot ln k versus 1 over T, you can find the activation energy using the slope, all right? So that's basically the relationship between the rate constant and the temperature. And just by looking at this equation, you can tell that with increasing temperature, everything else being the same, the activation energy, the molar gas constant, which is of course going to be constant, and if A is the same, then if you look at this equation, you'll see that as you increase the temperature, the rate constant increases. And if the rate constant increases, that means that the rate will increase, right? So basically, this equation basically shows you that when temperature increases, the rate will increase. Okay, let me say something about the collision factor A, or also known as the frequency factor. Basically, this takes into account two things: the frequency of collision and also the correct orientation of the molecules while they collide, right? So that's basically what A represent, right? Now, this part of the equation, so remember, just to remind you, K is equal to A times e to the minus EA over RT, right? So the A part is the frequency factor. So as I said before, it takes into account the collision frequency and the molecules having the correct orientation. The other part of this equation basically shows you the fraction of molecules that have sufficient energy to produce a reaction, right? So those are the two parts that come together to give you your rate constant. So the A part basically is a reflection of the frequency, the collision frequency and the orientation being correct when the molecules react. And the other part basically gives you the fraction of the molecules that would collide successfully to form products. Okay, so now I think we can do, let me get out of this here. The next question. So let me clear this here. So this question says calculate the activation energy for the decomposition reaction of NO2, and it gives you the equation. And it says that the rate constant at 300 degrees Celsius is 5.7 times 10 to the minus 1, n to the minus 1 seconds to the minus 1. And then at 230 degrees Celsius, this would be the rate constant, 2.7 times 10 to the minus 2. So what I'm going to do, scroll down here, I think I'm going to need some space. Now, let me remind you of the equation I just showed you. And that equation is K is equal to A times E to the minus EA over RT. Now, there's another form of this equation that you can derive based on getting two different temperatures and the corresponding rate constants, right? So let's say that at T1, the rate constant is K1, right? And let's say at T2, I'm going to write another equation here, K2 is equal to A to the minus EA over RT2, right? So at T1, the rate constant is K1. At T2, the rate constant is K2. So let's divide these two. What are we going to get? We're going to get K1 divided by K2. The A's are going to cancel out. And you're going to get, as a result, E to the minus EA over R times 1 over T1 minus 1 over T2. All right? So basically, we don't need A because A will cancel out here and here to get the relationship between K1, K2, T1, and T2. All right? So the reason why I derived this equation here is because if you look at this question, they gave you an initial temperature, so I'm going to call this T1. They gave you the corresponding rate constant, so I'm going to call that K1. This would be T2, and the corresponding rate constant would be K2. And what's the question asking for? The activation energy, right? Which is this right here. So the question is, how do we get the activation energy? Well, we could find the natural log of both sides, right? When we do that, you're going to end up with ln K1 over K2, and that would be equal to minus EA over R times 1 over T1 minus 1 over T2. And therefore, to get the activation energy, that would be equal to minus R ln K1 over K2 divided by 1 over, shucks, let me erase this here. One over T1 minus 1 over T2, right? So now, basically, we can plug all these values into this equation. Of course, R is 8.31 joules per mole Kelvin, multiplied by ln K1, which is 5.7 times 10 to the minus 1, m minus 1 s to the minus 1, divided by K2, which is 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1. And all of that will be divided by 1 over, what's T1? Oh, by the way, remember the temperatures have to be expressed in Kelvin. I forgot about that, right? So T1, when you add 273 to T1, that will be 273 plus 300, so that will be 573 Kelvin. And when you add 273 to 230, you're going to get 503 Kelvin. So 1 over T1 is 1 over 573 Kelvin minus 1 over T2, which is 1 over 503 Kelvin. So that's basically the setup. So now we have to do some number crunching. What am I going to do? I'll work out this part first, the denominator. So 573 minus 503. Okay, so this part I got minus 2.43 times 10 to the minus 4. Again, please correct me if I'm wrong, but that's what I got for the bottom part, right? K to the minus 1. Now for the top part, I'm going to do this part here. So 5.7 times 10 to the minus 1 divided by 2.7 times 10 to the minus 2. And then I'm going to find a natural log of that. And then I'm going to multiply that by 8.31. And what I got up here is minus, how many sig figs? 3 sig figs. So minus 25.3. All right. Now in terms of units, and this will cancel out with that. So the units remaining will be joules per mole Kelvin. All right. So let me do this calculation. So the negative signs will cancel out. So 25.3 divided by 2.43 times 10 to the minus 4. And I'm going to roll this out to 3 sig figs. So according to my calculations, I got 1.04 times 10 to the 5. And the units here would be, well, the Kelvin units will cancel out here and here. So the units in the final answer is going to be joules per mole. And that's basically how that is done. All right. Okay, any questions about this one? Yes, ma'am.
Is that a 2.43 or 9.3 at toward the end?
2.43.
Okay.
2.43. All right, any other questions about this one? Any other questions? Any other questions? Okay, let me see if we can do the next one. No, we can't do that. Okay, so let me go ahead and clear this. And let me go back to the PowerPoint. So now we're going to talk about, again, something that will become important for those of you who have to do organic chemistry. So this will form the basis of mechanisms that you'll discuss in organic chemistry. Again, for those of you who have to do organic chemistry, right? Now, as you can imagine, when it comes to most chemical reactions, what you'll find is that a chemical equation only gives you what you start off with and what you end up with. It doesn't tell you about the steps that occur in between, right? The steps that occur in between as you go from reactants to products, in chemistry, we call that the reaction mechanism, all right? And understanding or determining what the reaction mechanism of a reaction is very important. For example, if you understand the mechanism of a reaction and understand all the features, all the molecular features that would affect the mechanism of a reaction, then you can, for example, understand, for example, let's say, what will happen if you lower the temperature? Would that increase or decrease the amount of products, all right? Or if you change the structure of one of the reactants, how would that affect the rate of reaction and so on? Or what type of catalyst you're going to use in a particular reaction. And this is particularly important in organic chemistry, as you're going to see, all right? So let's talk about reaction mechanisms. As stated here, you can have an overall reaction, but basically for most reactions, you can have a series of steps. There are few reactions where it's a one-step process, but most reactions, you have a series of steps. And these steps are called elementary steps or elementary reactions, right? So the sequence of elementary steps that leads to the product from the reactant, we call that the reaction mechanism. So here's an example, a very simple example of an overall reaction, right? 2 nitrogen monoxide molecules reacting with 1 oxygen molecule to form 2 nitrogen dioxide molecules, right? And then somebody did some experiment and they detected this molecule as the reaction is progressing. So therefore, whatever mechanism that you put forward must include the formation of that molecule. So one possible mechanism of this reaction is where you have 2 NO molecules coming together to form this species, dinitrogen dioxide, all right? And then what happens next is the dinitrogen dioxide will react with the oxygen molecule to form the final product, which is nitrogen dioxide, right? So this is an example of a mechanism of a reaction. And one thing you need to understand is that mechanisms are theoretical concepts which can be tested, right? So one can come up with a mechanism for a reaction, and then that person or somebody else can test that mechanism by altering, certain features to see if the mechanism will be supported by further evidence, right? Now, one thing that must always happen when somebody proposes a mechanism is that when you add the different steps of the mechanism, the final result should be the overall equation. And in this particular case, that is the case, right? Because in this case, the N2O2 will cancel out here and here. And then when you add up what is left on the left and right side of the equation, you're going to end up with the overall equation, which is 2NO plus O2 to give 2NO2, all right? And that is true for all mechanisms. All mechanisms that anybody would put forward must add up to give you, in the final analysis, the overall equation, all right? So this is just a pictorial representation of the mechanism where you have the two NO molecules coming together to form N2O2, and then N2O2 molecule reacts with the oxygen to form the final product, which would be 2 molecules of NO2. Okay, a couple of things we need to say about mechanisms, right? In the mechanisms, you have certain species that are called intermediates. The intermediates are those species that would appear in the mechanism, but do not appear in the overall equation. And the reason why is stated right here. The intermediate is always formed in an earlier step, but used up in a subsequent step, right? So that's what an intermediate is. An intermediate is a species that is involved in a mechanism where it is produced in an earlier step, but used up in a subsequent elementary step, all right? So going back to this example right here, the intermediate in this case would be the N2O2, right? Because it is formed in a previous step and used up in a subsequent step. So that's the reason why they cancel out, and therefore they do not appear in the final equation, all right? Another term I need to introduce to you when it comes to reaction mechanism is this term molecularity, right? The molecularity of a step is basically the number of molecules that are involved as reactants in that step, right? So in the case of this step right here, we have 2 molecules involved, right? So we say that the molecularity of that step is 2. And the same is true for this step. But there's some other terms that relates to the molecularity of a reaction. So we say that the step is unimolecular if there's only 1 molecule involved. The step would be bimolecular if there are only 2 molecules involved. And then there's this term molecular, if 3 molecules are involved in an elementary step. The thing is that you need to realize that the likelihood of 3 molecules colliding at the same time is almost 0, right? So therefore, it's very unlikely that any mechanism will involve a third molecular step, right? Most reactions will involve either 1 molecule involved in a particular elementary step or 2 molecules where they collide. But for you to have 3 molecules colliding at the same time, I mean, if you think of, 3 persons throwing up basketballs and they collide simultaneously at the same time, it's highly unlikely, right? So the term molecular reaction is it's a theoretical concept, but very unlikely to occur, all right? So based on the elementary steps, we can simply write down the rate laws. What time is it, by the way? Okay. We can write down the rate laws for these steps, and it's very simple. So let me show you what happens in the case of a unimolecular reaction. This is the equation here. The rate law is simply rate is equal to K times the concentration of the reactant of that step, right? In the case of a bimolecular elementary step, we can, let's say you're 2 different species colliding. Then the rate of that step is equal to K times the concentration of A times the concentration of B. Here's another bimolecular reaction where the 2 reacting species are the same. In that particular case, the rate will be equal to K times the concentration of the reactant squared, all right? And that's as far as we're gonna go. We're not gonna go into the term molecular for the reasons I mentioned before, all right? So basically, that's how we determine the rates of the elementary step based on whether or not the reaction or that step is unimolecular or bimolecular. Now, when writing plausible reaction mechanisms, as I said before, the sum of the steps must give you the overall equation, right? And here's a term I'm going to introduce to you. In fact, I think I have the definition on the next page, or maybe below here. The rate determining step should predict the same rate law that is determined experimentally. So the question is, what is the rate determining step? The rate determining step is the slowest of the individual elementary steps for the overall reaction, right? So basically, you're going to have several steps in a multi-step process, and one of them would be the slowest step, and we call that step the rate determining step. In some textbooks, they call it the rate limiting step, all right? And in both cases, the reason why they're called such is that the rate determining step determines the overall rate of the reaction, right? So the rate of the reaction, the overall rate of the reaction cannot proceed faster than the rate determining step, all right? Okay, so basically these are the steps for determining or studying a reaction mechanism. You do your experiment, get your data to determine the rate law, and then after you determine the rate law, then you postulate a mechanism, a possible reasonable reaction mechanism for the reaction. And that's basically what kinetics is all about, especially when it gets to research, all right? Okay, so let's look at this example. It says here that the experimental rate law for the reaction between NO2 and CO to produce CO and CO2 gives you this. This is the rate law for that reaction. Rate is equal to K times the concentration of NO2 squared. So somebody did the experiment and got this rate law. And then it says the reaction is believed to occur via two steps. Step one is where two molecules of NO2 react to form NO and NO3. And then step two is where NO3 react with CO, to form NO2 and CO2. So the question is asking, what is the equation for the overall reaction? Well, we can get a hint to that answer by looking at the rate law. The rate law says rate is equal to K times the concentration of NO2 squared, right? So basically, that is the same as a rate law for this elementary step, right? Oh, I'm sorry, I misread the question. The question is asking, what is the equation for the overall reaction? To answer that, we look for what will happen when you add these two equations together. So my question to you is, when we add these two equations together, what, if anything, will cancel out?
NO3.
The NO3s will cancel out, exactly. So, sorry. So the NO3 here and here will cancel out, and you just add what is left. Oh, and also one more thing will cancel out, NO2, all right? So basically, you cancel out all common items on both sides, and you're going to end up with your overall equation. The next question is, what is the intermediate? Now, let me remind you of what the intermediate is. The intermediate is a species that is produced in one step and then used up in a subsequent step. So based on what we have here, what would you say the intermediate is?
NO3.
Exactly, so that's the correct answer, NO3. Come on. All right? Right, so NO3 would be the intermediate. The next question says, what can you say about the relative rates of step one and step two? And that was a question I was about to answer earlier. So what can you say about the relative rates of step one and step two? In other words, what the question is asking for is which one, based on the rate law, which step is faster or which step is slower? Or let's deal with faster. Which step is faster?
Two.
Why do you say step two? What's the rate equation for step 2? Rate is equal to what? Oops.
KA,
I'm sorry?
it's K
K times,
A times B,
huh?
no? Is it,
Those are the two species involved as reactants.
3
NO3
times?
times CO, right? So what's the rate equation for the first step? K times concentration of NO2
Times
to the squared, right? So which one would you expect to be the slowest step? Hint, hint. Which would you expect to be the slowest step?
first one.
The first one. Remember what I said earlier. The slowest step is the one that determines the overall rate of reaction. So since the overall rate is given by that equation here, and the first step has the same rate law, right? That means that it doesn't matter what the second step is in terms of the speed, because it's faster, right? So therefore, the answer is that, what can you say about the relative rate of step 1 would be slower. Let me see what the answer is here. Or step 2 would be faster. Right, so step 1 would be slower compared to step 2.
Or if they don't give you the rate law, like how would you know?
Well, that means that you would have to do something else to determine which is slower. In some questions, they actually give you that the fact that one step is slower than the other. In fact, one of the assignment questions, let me clear this here. Just to give you an idea as to what kind of question you could be asked. Going back to the assignment. Okay. Let's look at number 8. It says consider the following elementary reactions. And it gives you this, and it gives you this. And let me just say, because I couldn't distinguish clearly between these two letters. This is I. This here is I. And this is I, right? This is HCl, this is HClI, all right? So just to clarify the formulas there, all right? So the question is, it says consider the following elementary reactions. What is the molecularity, of each reaction, and write the rate law expression in for each, all right? So for A, what's the molecularity? Now remember, the molecularity is the number of molecules that are involved as reactants in the elementary step. So for A, the molecularity will be equal to what?
2.
Exactly. And what would be the rate law? Rate is equal to what?
K
K
times CO
times the concentration of CO.
times the concentration of CO2.
Exactly. All right. Okay, good. What about B? What's the molecularity?
1.
You sure? Yeah, you're right. I'm just pulling your leg. Yeah, it would be 1. All right. And what would be the rate law for that step?
K times HClI.
HClI. Oops. All right. Okay. So that's it as far as number 8 is concerned, I think. Oh, okay, yeah. Any questions about this? Any questions? Any questions? Okay, let me clear this.
Excuse me,
Oh, yes.
can you explain molecularity again?
Okay, so the molecularity is the number of molecules involved as reactants in an elementary step. So the mechanism will have several steps, right? And you look at the number of molecules involved as reactants in each step. And that would be the molecularity of each step. All right? Okay. So any other questions before I move on? Any other questions?
So for like that, if you were trying to determine which one was slower,
Well,
It would
these are two different steps for two different mechanisms, so we can't use this. But you're gonna see how this works in, I think the next example, but, any other questions about this? Any other questions?
For step B, is HCl and I in the same bracket?
Oh, you mean, yes. Let me make that clear.
And why is that?
Well, because that's this right here. That's the reactant. So yes, this should be in parentheses, square parentheses here. All right? Okay. Any other questions? Any other questions? All right, let me clear this. And let me scroll it down. Okay, so here, I think this is where you're going to see what you were asking just now, right? They gave you a mechanism, right? This is a three-step mechanism for a reaction, right? So, and in this case, they told you that this is a slow step. So they give you information that this first step is the rate determining step, right? All the other steps are faster, so therefore the overall reaction rate will be based on and limited to the rate of this step right here, all right? So the first question is asking, identify intermediates and, okay, catalyst. All right, tell you what, stick a pin for this one because I need to talk about catalysts before we can do this question. I'm sorry about that. Okay, so let me go back to the PowerPoint slide. All right, so a catalyst. What's a catalyst? I'm quite sure if you have done biology courses, then you'd have met enzymes, right? Enzymes are naturally occurring catalysts that exist in biological systems, right? So what a catalyst is, it is a substance that increases the rate of reaction, but remains unchanged at the end of the reaction, right? So basically the enzyme involves itself in the reaction, speeds up the reaction, and then it's regenerated, all right? So basically what we're showing here are two energy diagrams, one for a catalyzed reaction and the other one for an uncatalyzed reaction, right? Now, the way the catalyst works is that it involves itself in the mechanism of the reaction, and the resulting mechanism will have a lower activation energy, all right? Remember, the activation energy is the minimum energy that the reacting molecules need in order for the reaction to take place, right? So if you think about it, use your imagination, right? Let's say you have a reaction that is uncatalyzed, right? Only a fraction of those molecules will have that minimum energy needed, right? Now, what happens if the activation energy is lowered? Everything else being constant. What happens when the activation energy is lowered? That means that more molecules will have now the new minimum energy required for the reaction to take place. And if more molecules have at least that minimum energy that has been lowered, then the reaction rate will increase. And that's what's being demonstrated here. For the uncatalyzed reaction, this is the activation energy. For the catalyzed reaction, the activation energy is lowered, right? And based on this equation here, if the activation energy is lowered, that means that the rate constant will increase, which would mean that the rate of the reaction will increase, all right? So here stated that if the activation energy is lowered, which is what happens when you add a catalyst to the reaction, then the rate constant will increase, which would mean that the rate of the reaction would increase, all right? So the rate of the catalyzed reaction will be greater than the rate of the uncatalyzed reaction, all right? Okay, so that's basically what happens when a catalyst is involved in a reaction. And also, of course, the activation energy of the catalyzed reaction will be lower compared to that of the uncatalyzed reaction. Okay, so there are two general types of catalysis. One is known as a heterogeneous catalyst or catalysis, where the states of the reactants and the state of the catalyst are different, right? And usually the state of the catalyst is a solid, and the state of the reactants would be either gaseous or aqueous or liquid, right? So one important example of this is the Haber synthesis of ammonia, right? Another one is the Ostwald process for producing nitric acid, and a third one, which is involve catalytic converters, right? So if you're driving a car, then your car or automobile will have that as a part of the exhaust system, all right? So that's what happens in the case. These are just examples, I should say, of heterogeneous catalysis. And then you have homogeneous catalysis, where the reactants and the catalysts are in the same state, usually liquid. And usually there are two types of catalysis in this regard. You have acid catalysis and you have base catalysis. And we'll probably talk about these shortly. But going back to the heterogeneous catalysis, what you are seeing here is a diagram which shows you what happens in the Haber process. The Haber process, as I said before, involves the formation of ammonia from nitrogen and hydrogen. So this is the reaction. N2 plus H2 to give 2 NH3, and to balance this, we're going to need a 3 here, right? So this is the Haber process, right? Now, if you take nitrogen gas and mix it with hydrogen gas, nothing is going to happen, right? But if you add a catalyst, then you're going to have the reaction between the nitrogen and hydrogen to form ammonia. And this guy here, Haber, he did a lot of work in terms of using different catalysts in order to carry out this reaction. His work was important back in World War I because at the time when he was a German chemist, by the way. At the time, they needed fertilizers to grow crops and so on, and they also need ammonia to make explosives for the war effort. And the source of nitrogen before came from South America, but because of the war and the shipping lanes being affected, they have to come up with a process for making nitrogen so that they can make their own explosives in Germany. So he got to work. He was commissioned to do his research to make ammonia using catalysts. So he came up with different combinations, and he found a combination that works. And this is how it works, right? Basically what happens is that on the surface of the catalyst, right, you're going to have what are called active sites. And these molecules, the nitrogen and the 3 hydrogen molecules, will be attracted to the active sites and bind to the active sites. And the term for that is adsorption. Let me write this down. Adsorption, not to be confused with absorption, right? Adsorption, right? Adsorption is where you have the molecules or the atoms clinging to the surface or attracted to the surface of the catalyst, right? When that happens, that weakens the bond between the nitrogen atoms in this molecule and the hydrogen bonds, the bonds of hydrogen in this molecule, right? So the atoms become separated and they can move along the surface of the catalyst, and then you're going to have a situation where one nitrogen atom will meet up with 3 hydrogen atoms, and then that will form the ammonia, right? And then the ammonia will be released from the surface of the catalyst. So that's basically a pictorial description of the mechanism of this particular reaction. Another important in terms of historical context about this reaction is that, or actually this researcher, Haber, was that he was a Jew. So by the time Hitler came around, he had to haul ass out of Germany because, of course, we all know what Hitler's attitudes towards Jews were concerned. You know, so regardless of what he did for the country, he had to leave the country because his life was at risk. All right. Just goes to show you that sometimes patriotism doesn't work out. Sometimes. All right. Okay. So that's an example of a heterogeneous catalysis, right? So this is the equation right here. And I think I have the combination of materials that he used to make the catalyst. So he experimented with a lot of stuff, and then he came up with this as the best way of making ammonia. He also looked at the effect of temperature as well and pressure, right? So he basically, tried, different pressures and temperatures, and he came up with the right combination that resulted in the formation of ammonia. Another example of, let me clear this here, another example of a heterogeneous catalysis is the Ostwald process. And it's a two-step process actually in terms of reactions. So the ammonia that is used to react with oxygen forms NO, and then the NO, and the catalyst that is used is platinum in this case, and then the NO is reacting with oxygen to form NO2, and then what happens next is that the NO2 is added to water, and two products are formed, nitrous acid and nitric acid. So this is a bit more complicated in terms of the number of steps involved, but the important point I'm trying to make here is that, again, this is an example of a heterogeneous catalysis because platinum is a metal and ammonia and oxygen are gases, all right? And finally, when it comes to heterogeneous catalysis, I should say, I mentioned catalytic converters. If I remember correctly, the material that is used to make catalytic converters, one is platinum, and the other one, if I remember correctly, is rhodium. And there's like a proportional combination of those two that is used to make this material, which basically is very important in terms of preventing poisonous gases escaping into the atmosphere after combustion of gasoline. So basically, the role of these of the catalytic converters is to convert carbon monoxide, which results from the incomplete combustion of gasoline, converted to something less harmful, right? By reacting carbon monoxide with oxygen to form carbon dioxide and water. So the catalytic converter catalyzes that reaction. There's also another reaction where nitrogen dioxide, which is also toxic, will be converted to something less toxic, right? And again, the material for the catalytic converter catalyzes that reaction. And I remember a couple of years ago, I've been seeing stuff online, and strangely enough, most of the news items I saw was on the West Coast, California and so on, where people have been stealing the catalytic converters because of the demand of platinum and rhodium, which are very expensive metals, right? So basically what has been happening over there in the West Coast, people, waking up in the morning and coming out, and when they start the engine, they hear this loud noise coming from their engine, and that's due to the fact that, these converters have been removed. And there was one case I remember reading where a lady was sleeping in her car, and she heard a noise, and she started her car and ran over the guy who was trying to steal the converter, the catalytic converter out of the car. So strangely enough, the news items I saw for that was on the West Coast and not over here on the East Coast. One final thing I want to mention, and I mentioned this earlier, enzymes, they are catalysts. And basically the way they work, there's a lock and key model that is used to explain how these catalysts work. Basically, this is the enzyme. The enzyme have active sites of a particular shape, so much so that they can accommodate a particular substrate. So the substrate can fit into that particular active site of the enzyme to form what is called the enzyme substrate complex. And then some bond breaking takes place, which results in the products being formed. And this is an actual example, and I don't remember exactly what this molecule is. I think it is amylase, which is the enzyme that you'll find in your saliva. So this would be representing a starch molecule. Here's the active site. So this fits right in here. And then after that, bond breaking takes place, and then you have simpler sugars being released. And this is just basically a plot of energy versus reaction progress for an uncatalyzed reaction where the substrate is converted to products. And then in the case of a catalyzed reaction, you see that there are two steps where this step here has a lower activation energy. This would be the rate determining step, but its activation energy will be lower than the uncatalyzed reaction, and therefore the reaction rate will proceed at a faster clip. And then this final graph here shows you the rate of reaction as it varies with the concentration of the substrate, and what you'll find is that the rate will increase until you get to a maximum value, which represents the fact that all the active sites in the enzyme are occupied. Okay, unfortunately, I think this is the end of the chapter here. Unfortunately, we did not get to, let me see. Okay, so question number 9 and question number 10 are the only two questions. Oh, and number 11. Number 11, I'm going to leave that for you to answer. You should be able to answer these questions. Basically, what number 11 is asking for is for you to describe the difference between these different terms. All right? And we did 12 already and 13. All right, so when we get back tomorrow, I'm going to start off by doing numbers 9 and 10, right? And let me just say that your upcoming test will be on Thursday, first test, right? And that test is going to cover the previous chapter of solutions, and colligative properties and all that, and this chapter right here, right? So it's very important that you turn in this when it's completed. I think I'm going to set the deadline for tomorrow, actually, so that I can grade it and get it back to you as soon as possible. Another thing I want to say is that you should receive, or you should have received, your graded assignment 1, right? If you have not received it, let me know as soon as possible. If you have not turned in assignment 1, please do so as soon as possible as well, all right? I have already posted the answer key to assignment 1, so you can use that to help you to review. And as soon as I grade assignment number 2, I'm going to send that back to you, and I'm going to also post the assignment 2 answer key as well. So you can have that as well to review, right? So make sure you do, if you have not submitted assignment 1 yet, make sure you submit that as soon as possible. And I think that's it by way of announcement. So that's it for today, folks. I'll see you guys tomorrow. Yes, sir.
I was waiting. I thought it was this even do anything to make millions.
All right. Yeah. But, the reason why. So long time.
Nothing makes hella money.
Because I wanted this to be free, to match up with that free, yeah. Yeah, exactly. Yeah, that's the reason why I did that, yeah. I'll talk about that tomorrow. Remind me, all right, okay. Yes, no.
So chapter 3 is going to be on test.
Go ahead.
We're starting chapter 3 tomorrow.
Yeah, what I've decided to do is just basically test you on the first 2 chapters.
Okay.
Right.
Okay,
Mhm.
thank you.
Yes, ma'am.
Will we have like equations on the test?
Any equations that will be provided would be in the packet that I've posted in Canvas.
Okay.
So I'll provide that for you. But the equations I mentioned earlier for the 0 first and second order, the concentration to time equations, and the half-life equations, you need to know those.
Okay.
Yeah.
And also, if we're going over the test that you posted, the past test, will that pretty much be what's going to be on the test? That kind of
Well, the topics, I'm not saying that the questions will be the same, but
those topics.
yeah, exactly.
Okay.
If you go through, if you review the assignments and if you review the past test questions, and I would strongly suggest that you try as many questions from the textbook as possible, you should be in good shape.
Okay.
All right?
Thank you.
Thank you.
Yes, ma'am.
Question.
Mhm.
For the lab, do we have to print out our own like?
Yes, you have to print out the handouts. So for this experiment that you'll be doing, which would be the colligative properties experiment, you need to print it from Canvas. Because each student need to have their own copy of the handout.
Okay.
All right?
And then I did have another question.
Yes, ma'am.
So I kind of was like confused, like when you were explaining one of the problems, I think it was question 7. I'm sorry, I didn't print out the thing. But when you were getting to like the formula, I understand you're supposed to use this one to like calculate that calculation energy. But how were you able to like get this equation right here where you split the time?
Oh, okay. So,
I didn't.
well, what happens is, there's some algebra involved. Let's use this here. So you're talking about, oh, I put up the tip, put up the thumb there. All right, let me use the board directly.
Okay.
So we had K1 is equal to A to the E to the minus EA over RT1, and K2 will be equal to A to the E to the minus EA over RT2, right? So the A's will cancel out. So basically, you're gonna get K1 over K2 is equal to E to the minus EA over RT1 over E to the minus EA over RT2, right? So in algebra, if let's say you have A to the X divided by A to the A to the Y, this will be equal to A to the X minus Y, right? So you have E to the minus E over RT1 and you have E to the minus EA over RT2. So that means that this will work out to be equal to
To the negative A minus.
E to the minus EA over RT1 minus EA over RT2, right? RT1, right?
Okay.
So you factor out minus EA over R, we're gonna get minus EA,
Oh,
Over
like you're
R.
distributing?
that's the term, I don't remember it. I did not back in the Stone Age, so
That's okay.
I don't remember the terms. But basically you factor out minus EA over R to get that out here, and you're gonna get 1 over T1 minus 1 over T2. So that's basically, how that is done.
What about understanding?
Professor?
Yes, yes, sir.
Quick little question.
Mhm.
So I was going over that same question.
Okay.
I actually got one, so
Right.
would that be 1.802?
Yeah, no, but what we have to do now, because, and that's the reason why I compare this to this, right? Because when you're adding, you round out to the lowest number of decimal places.
Right.
So when you add 1.8 to this, right, this has 1 decimal place and this has 4 decimal places. So basically, it's gonna end up being 1.8 anyway.
Yeah, and then I actually got 5.5 times 10 to the negative 4 instead of 5.1 times 10 to the.
All right, we can discuss that first thing tomorrow. And if there's any correction to be made, I'll make it. Yeah.
Thank you, Professor.
All right.